The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Alright, so I'm going to work through problem number 14 for the Physics 2020 Midterm Exam 1. And actually, problem number 14 is a continuation of problem number 13. So, if you haven't worked through problem number 13, it's probably a good idea that you work through problem number 13 first, or at least read through problem number 13. And so this particular problem says, how long does it take the ball to reach the ground after it is initially tossed into the air? So if you remember, we had a ball that was sitting on the build. Remember from problem 13, we had a ball that was initially tossed in the air on top of a 50-meter building with an initial velocity of 12 meters per second. And so this ball would reach its maximum height, and then now it's going to return back to the ground, and it's asking us to find that time it takes, that total time it takes for the ball after it's initially launched to reach its maximum height and then return back down to the ground. And so what is that time? Again, we set up our coordinate system with the positive y going up and the positive x going to the right. We know that since the ball is being launched from the top of the building, the initial y value is going to be 50 meters. We know that the mass of the ball is 2 kilograms, 2.0 kilograms. When the ball finally returns down to the ground, we know that final y displacement is actually equal to 0, if we assume that the ground is 0. All right, and a couple of things we know is that gravity is acting on the ball initially, so it's going to have a negative value because it's going to be slowing it down. And what else do we know? So that's the information that is given. Okay, so from the information that is given, we need to go to our formula review sheet to see if we can find the equation that will help us solve this problem with the information that's given. And so we have several options here. If you look under projectile motion, we know that this ball is moving, and the only thing acting on the ball after it's initially tossed into the air is gravity, so that's the definition of projectile motion. Really, we have nothing acting on it in the x direction, so we can kind of ignore all the formulas in the x direction. So we only have to consider projectile motion in the y direction. And there are several options here. But as we look through them, you'll see that there's an equation. We have two equations that have the parameter time in it. And so since we're trying to determine the time, we need to pick an equation. Well, it would be helpful if we had an equation that had the time in it. And so we look there and we see that we have, an equation for the final velocity, and we have an equation for determining the final y. But if we look at the equation with the final velocity, which we have Vy is equal to V sub 0 sine of the initial angle minus GT, one thing we know about this equation, or we don't know in this equation, is the final velocity. Okay, we don't know anything about how fast the ball is traveling when it hits the ground. We also don't know the time, since we're trying to find that. So basically we have two unknowns in this particular equation. Now we cannot solve this equation directly using the information that we have. We need to find out what the final velocity is before we can find out the time. And so let's try to see if we can determine another equation that might be more helpful. Okay, so it turns out that if we use this equation, turns out if we use this equation, we should be able to determine the time, because we know everything that has a check mark. We do know, okay, we know the initial velocity, theta, the initial angle, okay? So if you remember, theta is, okay, theta is the angle that the projectile makes with the horizontal initially, okay? And so since this ball is being thrown straight up, theta is actually this angle here, which is pi over 2, or 90 degrees. So we do know the initial angle. Okay, so we know that the initial angle is equal to pi over 2. So we do know that as well. And we also know gravity. We know that the gravity is acting down, which is the reason why there's a negative sign here. And if you're kind of confused as to when you're supposed to plug in a negative gravity and a positive gravity, please refer to the short lecture on signs for projectile motion and when we're supposed to use positive and negative gravity, and also a short lecture on these particular equations and how they came up with them and why you have some positive signs and some negative signs in these equations. So there's a little short lecture for this particular midterm exam that I think that if you're confused and you're getting your signs confused, will help to clarify when you're supposed to use plus and minus signs. It will help you set up your coordinate systems and basically understand the equations a little bit better. Okay, so having said that, all right, let's see. We can basically now rearrange this equation so that we get y minus y sub 0, okay, is equal to your initial velocity, okay, and the sine of theta, okay, so that would be the sine of pi over 2, okay, times t minus 1/2 gt squared, okay, and we know that the sine of theta is just equal to 1, all right, and so we can now substitute in the information, the numbers, into this equation and see if we can solve for the time. All right, so we know that the final y is going to be 0, okay, that's going to be 0 meters, minus your initial y, which is starting at the 50 meters on the top of the building, and we know that your initial velocity is 12 meters per second, and it's also important to know that velocity is a vector, so it has both magnitude and direction, and since we defined our positive y direction to be going up, if it has an initial velocity that's going up, that initial velocity is going to be positive. If the initial velocity was directed down, it would be negative, okay, so and then that's just times 1, so that's just 12 meters per second times your time minus 1/2 gravity. Gravity is actually acting to slow the object down, okay, so gravity is actually negative, but the negative is already accounted for in this particular equation with the minus sign out here, and so all we need to do is substitute in for gravity, which is 9.8 meters per second squared times your time squared. All right, and let's do a little simplifying and rearranging. So we just get minus 50 meters is equal to basically 12, and I'm going to drop the units for now. Okay, so that's going to be 12t minus 4.9 t squared. All right, and so since we want to solve for t, let's go ahead and rearrange this equation in this way, where we have 4.9 t squared would be a minus 12t and a minus 50 equal to 0. All right, and so what we've got here is basically a quadratic equation. And the way that we're going to solve this quadratic equation is, let's erase here to get some more room. Before I move further, remember from the equation we had y minus y sub 0, and we got that is equal to negative 50 meters. All right? And some of you might be confused as to how this particular equation that we're using, okay, is going to give us the total time for when it was the ball was initially tossed in the air to reach the ground. But if you think about it, okay, here's the object, all right, and the object is going to basically be projected up into the air, okay, and then it's going to come down and reach the same initial level and then keep going down to basically hit the ground. All right? And so in this particular equation, where you have you have y minus y sub 0 is equal to negative 50. That's the change in y. But you ask yourself, how can it be negative 50 when we started, well, it's at least going to travel 50 meters, but it's also going to travel the additional amount of distance to reach the maximum height, so that has to be more than 50 meters. Well, that's true, but the change is not the total distance traveled. The change is just the change in location between the initial location and the final location. And so that is just between this point and this point. And within this equation, as you can see, we have a parabolic shape here, okay? So this equation is a parabola since it has t squared, right? And in addition to that, we have an initial velocity that's pointed upwards. Okay, so this initial velocity is pointed upwards here at 12 meters per second. So embedded in this equation knows that the ball, because you're putting in the correct parameters with the correct signs, it's assuming that the ball is being thrown up, it's coming to a stop, then it's coming down, and then it's keep going further down to basically to hit the ground. And because that we have the change in y is only equal to 50, and we have the velocity that's basically headed up, we know that this is projectile motion. When we solve this equation for time, we're actually determining the total time of the projectile motion. All right? And so that's how we can use this equation in order to find the total time. So that's just a little side note. All right. All right, so we've got our equation here, our parabolic equation, our quadratic equation. So we're going to use the quadratic formula in order to solve for this. So that's just minus b plus or minus the square root of b squared minus 4ac all over 2a. And that's going to be our time. So substituting in the information, so we have a minus, so that's a positive 12, plus or minus the square root of 12, and let's carry the units now again, 12 meters per second squared minus 4. A, which is 4.9 meters per second squared. Remember, we just divided the gravity by 2. Times C, which is minus 50 meters. And that's all going to be over 2 times 4.9 meters per second squared. Okay? And so, this is equal to T. So, in this particular problem, we have meters per second, and that's going to be squared, so we have meters squared over seconds squared. And here we have a meters times a meter, so that's a meter squared over seconds squared. And when we take the square root of meters squared over seconds squared, we just get meters per second, which is consistent with this units here, so we can add them together. All right, so our units are consistent, and now when we calculate this, we get basically T is equal to 4.6 seconds. All right. You're actually going to get two values for T, right? So if I get my calculator out here, you're going to get two values for T. You're going to get a value for T that is positive, and you're going to get a value for T that is negative. All right. So you'll get 2T, so you get T is equal to 12 plus So this is one of the T's that you'll get. And then the other T is going to be 12 minus that. Okay? So here are the two T's. When you solve the quadratic equation that you're going to get. You're going to get 12 plus this and 12 minus that. All right? And when you do the 12 minus, this is going to work out to be a negative number. Okay? Well, there's no such thing as negative time. It has no physical meaning. So we ignore this one, and then this one will work out to be the time is equal to 4.6 seconds. It is a quadratic, so you're always going to get two values for T. Sometimes they could be both positive, which will have different meanings. But if you give a time that's negative, we know that we can throw that away because there is no such thing as negative time. And so the answer is actually 4.6 seconds it takes total for the ball after it's initially tossed to reach its maximum height and then hit the ground.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.